Recording started.
Now you can't see the camera anymore. Good evening, everybody. I do want to welcome you to another session of organic chemistry. My name is Professor Ayorinde, for those who are just coming for the first time today. Okay, so today we are going to finish up on chapter 14, and if we have enough time, start with chapter 15, as if you guys do not ask too many questions. Okay, now, but before we start, I do have a couple of announcements. I'm sure some of you got the email that I sent out today. Our own work assignment has been assigned for the end of chapter 14, problem set. That would be the own work assignment for this chapter. And it is due on Thursday, next Thursday. That is January 19 at 11 p.m. Okay, also, our first online review session will be next Wednesday. The online review session will be next Wednesday. Every week we are going to have an online review session in which we go to problem solving. And the time will be 7 p.m. Generally, this lasts for about 90 minutes. Okay, so we start next Wednesday at 7 p.m. I will send you the link to that session by email as a reminder next week. Okay, when we left, the last time we left, we were doing Diels-Alder cycloaddition reactions. So what we want to do now is to continue this series of reactions. Okay, so we have Diels-Alder reaction. This is a very important set of reactions indeed. As a matter of fact, the 1950 Nobel Prize winners were both Diels and Alder, the two scientists who actually discovered this particular reaction. This reaction allows us to form two carbon-carbon bonds at the same time. As you can see in this example here, you have a conjugated diene reacting with a carbon-carbon double bond, you see here, and it's a one-step reaction in which you are going to form a six-member ring. To give you more about the stereochemistry, let us talk about the stereochemistry of the Diels-Alder reaction. Say, for example, you start with this molecule here. Of course, this is your diene. And if you start with this dienophile, say you start with this molecule here, you notice that we are starting, this is the dienophile is a cis. It's a cis alkene in which the substituents are on the same side. These two substituents here, this cyano group and this carbonic group, are on the same side of the carbon-carbon double bond. Now, if you now perform a Diels-Alder reaction, of course, you are going to get a six-member ring. In which the double bond is now here. Keep in mind that essentially what you are getting here for the Diels-Alder reaction mechanism this attacks this here. The pi electrons attack that carbon. Of course, now this moves to here, and all of these things are happening at the same time. And now this pi electron goes here. So this is what we call a concerted reaction mechanism. Okay, so now you form this product. In which the stereochemistry here is that in which the cyano group and the carbonyl group here, the acetic group, are on the same side of the ring. In other words, this reaction is stereospecific. Meaning that you only form a particular isomer, stereoisomer. So, in other words, if you start with a cis dienophile, if your dienophile is cis stereochemistry, these two groups that are on the same side, that stereochemistry will be maintained in the product. Okay? If on the other hand, we start with a trans, if we start with a trans, and we perform our Diels-Alder reaction, what do you think the stereochemistry of the product will be? Trans, exactly. Okay, what the Diels-Alder reaction does is to maintain the stereochemistry of the starting material. So here, and this here will be coming at you. So we say this the Diels-Alder reaction is stereospecific. Now, if, for example, I give you this molecule here, if I give you that diene, and I want you to perform a Diels-Alder reaction, say we have this, the Diels-Alder reaction will not work with this conformation here. This is what we call trans conformation. The Diels-Alder reaction will not work. In other words, this is what you have here. Okay, what have the conjugated diene that I've given you? You have a double bond, you have a double bond. So this conformation is what we refer to as the trans conformation. So in order for you to make the Diels-Alder work, you have to rotate the single bond that joins the carbon-carbon double bond. So you form the cis conformation. This will be the cis conformation. Okay? So therefore, in this case, what you have to do is to simply take if this is what I give you and I ask you to give me the product of the Diels-Alder reaction, well, let me make it a little bit more complicated. Supposing I have this here. Okay? And you have this here. Say we have bromine here, for example. Okay. Now you notice the relationship between the methyl and the bromo group. Now when you rotate this, you have to rotate this here, that single bond that joins the carbon-carbon double bond. Okay, so now you get now you notice that the methyl and the bromo, you could almost think that they are trans to each other according from the trans conformation that we're giving you here. But once you rotate that, that means now they will now be cis to each other. So you are going to rotate this. So this bromine now will be here, and this methyl will be here. So at this point, we will now think of the substituent on the 1,4 carbon atoms will now be cis to each other, because this is going out, this is also going out. Okay, so that is as a result of the rotation. Once you do the rotation, now you could now perform your Diels-Alder reaction. So now you now take this, by the way, this conformation is what we call this cis conformation. We refer to this as the cis. Okay, so this is the trans, this is the cis. We perform the Diels-Alder reaction using the cis conformation. And what will be the product? The product will be, start with your 6-member ring. Okay. Now, what do you think the stereochemistry is going to be here? Let's start with the this cyano group and the methyl group, which will be on this side. What will be the stereochemistry between them? Cis. Okay. So this will be and this one here will be on the same. And with relation to the dienophile, the substituent on the dienophile, what would be the relationship in the product? Because they will be here and here. They will also be cis. Okay, very good. So therefore, what we have in the Diels-Alder reaction, the stereochemistry of the starting materials are preserved in the product. So, oh, I'm sorry, thank you. Okay. So the stereochemistry of the starting material are preserved in the product, in the Diels-Alder product. Okay. So if you start with a dienophile that is cis, the substituent will also be cis in the product. If you start with a diene that's trans, the substituent will also be trans in the product. Yes, there. To do what? The oh no, you don't need to draw the arrows. Just a minute. So are you saying that I should draw the arrows? You want to see the arrows? Okay. Good. But you don't have to do that. But you just want to see it. Okay, what is happening here? Of course, this is going to here. In other words, this carbon is going to attach itself to this carbon, and this pi electron will move, attach itself to this carbon, and all of these are happening at the same time. And then this pi electron will simply move to. So in essence, you're almost forming a six-membered transition state. You could almost think of it this way, joining this here and joining this here. Okay? That is very good. That's a good question, by the way, because it does allow you to to be able to determine what the product of the reaction is. Yes.
How do you know the variability of the coming out?
Okay. I mean, in the dienophile right here, right in this molecule here, right? Okay. At this point, if you look at this here, this is going out, right? And bromine is also going out. So in that case, you say they are cis. Okay? Now, if on the other hand, say for example, on the other hand, this is what you have. Supposing we have this, okay, if I have this, the bromine, right, okay, and this is here, then based on what I see in the dying right here, I would say the relationship between this methyl and this bromine would be trans, because this is going out and this is coming. The bromine is coming in and the methyl is going out, so that would be trans. Okay?
I mean, I understand that part. I'm saying, I understand that the methyl and bromine are like sitting to each other.
Yes.
But their relationship with others.
Oh, I got you. The relationship with okay, now I see the question here. The question you are asking is, what is the relationship between this methyl and this cyano? Okay. And this here and here. Actually, you do get a mixture, because you do get a mixture. It's a lot more complex than that, so you do get a mixture, yes. Very good question, yes.
So with the, so when you drew in the green, would we have to rotate that one to react it, or could we do that with the reactor?
Oh no, you do not, because this is already the conjugation, the double bond is already in the cis conformation.
So that is the double bond.
Yeah, as long as the double bond is in the cis conformation, that's all you need for Diels-Alder. Okay. Now, also, if you have, since you asked that question, supposing we have this. Supposing we have this. If both of those are now they are cis to each other, like this, this type of molecule is very difficult to undergo Diels-Alder reaction because of steric problem. They're bumping into each other. So this here, for the most part, will not undergo Diels-Alder reaction. So the best Diels-Alder reaction is for you to allow some kind of either the substituent on carbon number 1. This is 1, 2, 3, and 4. Those substituents must be trans to each other, or if they are going to be cis, they will have to be outside of the double bond system, the conjugation system. Okay. Because if you have them here being cis to each other, just as we have here, the Diels-Alder will not work. Okay. Now let us. Any more questions? Okay. What I want to do now, I want us to start doing some problems. Yes. Yeah, Tony, go ahead. Oh, so this molecule here will not undergo Diels-Alder reaction because this methyl and this bromine, they are bumping into each other, and they will not allow the movement of electron, okay, and because of steric problems. Now, let us start doing some problems. What I've done now, I've got some problems from the back of the chapter 14. And so we are going to see some of these problems and see how we can deal with them. These are typical problems that you will probably encounter in your quizzes and your examinations. And I will tell you, many of these problems in the back of your text are really very good problems. So I will advise you to actually go through each one of them. Okay, so now let us see what we can do with this. Okay, Jessica, go ahead and read this question for us.
How can you use the Diels-Alder reaction to prepare the following product? Starting buying.
Okay, very good. Okay, so now what they are asking you to do here is to make this product, this compound, using Diels-Alder reaction. Okay, using Diels-Alder reaction. So let us try. Let's start with A. Does anybody have an idea? What will be the starting material for compound A? What will be the starting material for compound A? Yes, that's right. What's your name? Oh, you are going to ask a question? Oh, you're thinking. Oh, okay, okay. Anybody has an idea? Okay. Yes, you need a diene and you need a dienophile, okay? Okay, yes. Nice, yes. Which 4 carbon? Double bond? Okay, oh, I see. Cut it in half? Which one? This one here? Okay, cut it in half? Okay. Okay, what do you mean by cut it in half? Okay. Okay. You want me to cut it in half like this? No, but you say we want to show the starting material. Okay.
How do you get that? If that's the product, I'm saying how do you get that?
Yes, okay. Right. Right, okay. So when you say cut it now, I will cut it here. I'll cut it here. Is that what you mean? Okay, very good. Now, let me give you one hint. When you have this kind of problem, you know that the Diels-Alder reaction, what does it do? It gives you a 6-member ring. Okay? So look at that molecule, whatever molecule you are given. Look at the 6-member ring that could possibly be the product of Diels-Alder. And then look at where the double bond is. Okay? So look at where the double bond is. Look at the possible 6-member ring. So if I do that, I say, okay, I have this 6-member ring right here. Right? You see that? I have that 6-member ring. Then I have a double bond here. So I will say this is where the dienophile must be coming from. Okay? So if that is the case, then all you need to do, just like you said, Mike, is simply just split this here and split this here. Okay, you now say, okay, since the double bond is here, the original double bond must be here and here. So the starting material for compound A will be, okay, that will be the diene. Do you see that? So that will be the diene. Now, what will be the dienophile? The dienophile is only a double bond, yes.
The rest of that molecule, like
exactly. The rest of the molecule, in other words, the rest of this molecule here, this here, will be where your dienophile is, right? Your double bond. Okay? And keep in mind that the original double bond will be on the opposite face to where the new carbon-carbon double bond is. So therefore, we say the double bond must be here. Okay, you see that? So, what do? We say, okay, that is the case. Therefore, that must be the dienophile. You see how easy that is? Oh, I'm sorry, yeah. Okay, so that must be your dienophile. You see that? Okay. Okay, let us do the B. Let's do B. Everybody got A? Okay. So, okay, let us now do B. Okay, B. Okay. Okay, where is the 6-member ring? This recycling 6-member ring. Where will it be? Where is it? This here? Forget the bridge, right? Let's go to the bridge. You see? So ignore the bridge. This bridge here, ignore it for now. Okay, that is the 6-member ring from Diels-Alder reaction, right? Okay, so if that is the case, so that means, therefore, we're going to split that. We simply say, okay, we cut it here, we cut it here. So that part will be where your dienophile is, right? Now keep in mind this bridge is here. So now we say, okay, if that is the case, keep in mind now that your double bond must be here, because the new double bond is here. Then the other double bond will be here because of the conjugation, right? So therefore, what do? I have yes. Okay. Just a minute, I will do that. Okay, so now you have this. So you say your double bond is here. That double bond is here. Okay. Now this bridge, now you bring this bridge in, and that would be that. That is that bridge right here. Okay. So now let me go ahead and number for Ashile. Okay, so we have this here. So this will be your diene, okay? But before I do the numbering, therefore your dienophile must be this part of the molecule. You see that? Must be this part of the molecule. This here must be your dienophile. Okay, Mike, yes, you have a question? Yes. Yes. But this is the starting material. You see, the product is a 6-member ring. Okay? So now, therefore, we say this is the dienophile is here. So therefore, that would be a double bond. A double bond with say cyano group. Okay? So that would be the dienophile. Okay, now how do we get the 6-member ring? If you just join this, right, and you join this, you see the 6-member ring? This here, let us now number this, and of course this double bond will go here. So now we number that, we say, let's use the black pen. Where do we want to start number? Say we start from here. 1, 2, 3, 4, 5, and 6. Okay, let us number on this side also. So now if we say that is, so now keep in mind this is now our 1. This here, this carbon here is 1. This carbon here is 2. This carbon here is 3. This is 4. Okay. This is 5. And this is 6. Okay. You see that? Now the bridge, which is this one here, the bridge is, let's call that 7, which is this here. You see that? You guys see that? Ashine? Is that okay? Okay. Everybody see that? Okay. Okay, so the question that was asked of us is to give the starting material for this product. And the starting material therefore will be The two starting materials will be this. This is the diene, and this is your dienophile. Okay? You follow that? Okay, now let's do C. Let's do C. I will tell you for C, there is a couple of Diels-Alder reactions. You can see now, you begin to see the importance of the Diels-Alder reaction. It does allow us to form very complicated molecules. Okay, so let us try C. Yes, go ahead. What's your name? Patrick? Okay, Patrick. Oh, you're trying to solve this problem for us? Okay, yeah, okay, go ahead. We say you have two, okay, very good. So you have two diene, you said two diene, very excellent. Okay, so the analysis you want to do here, right? Since Patrick is now giving us the answer. So you have this 6-member ring, right? Okay, we know that the Diels-Alder is coming from here because you have this double bond here, right? And then another Diels-Alder coming from here because of this here, right? So if that is the case, okay, so are you telling us that we just clip this here and here, and this part becomes the diene part? Okay, very good. So we have the diene. Okay, very good. So therefore, on this part, will be your dienophile will be on this carbon. Sorry about that. For the dienophile, the double bond will be here, right? Is that what you say? Okay. So therefore, you say that will be here. Everything else is here. The carbonyl is still here. This carbonyl is still here. Okay? And that means this part of the molecule, let's see here. Okay. Let's do one step at a time. Okay? Okay, so this will be your diene right here. And this is your dienophile, right? So if we join this, we join this carbon to that carbon, and this carbon to that carbon, and of course the double bond moves to here, then you form this product, right? That's how we form that product. Everybody follow, see that? Okay, very good. So now, that is the first Diels-Alder reaction. Now the second one, yeah, that would be the second one. The first one would be, now let's do the analysis. Yes, Karen. No, this is the second one. Okay, you see why in a minute. Okay. Okay, now let's take a look at this this product here. Okay, in other words, this is another product that came from an earlier Diels-Alder reaction. So let us do the analysis of that. If we say this part of the molecule will be coming from Diels-Alder, so we could clip that. Say, okay, this here and this here. So therefore, what will be the starting material? So we could very well say that in this case, the double bond will be here for the dienophile. So that would be this here. Okay. And then the diene will be this. Okay, Karen, do you now see it? Okay. This diene here reacts with this with this dienophile to form this product. Okay, now once that product is formed, another molecule of the diene now comes, reacts with this carbon-carbon double bond, and that is how we get this here. Yes.
I have two questions. So if we attack from the left, can reactions start from the left?
Yes, I mean it's the same thing that is happening.
How come you can't just do one? Like have it be one diene and then
yeah. Yeah, very good question. If that the way the question is asked of you, you could very well do that. Okay? I mean, since you could say that is your starting material. You could say that this here, you could very well say that this. You see, what Emma is saying is this could very well be your starting material, and this starting material, and then you end it just. That's the end of it. So you don't have to make this. But here I'm simply showing you that you could also make this. Okay? Everybody follow that? Yes. Myra. Yes, nothing stops it. But don't forget the product that you're supposed to make. You see, you have to look at the product you have to make. Actually, this could be, Myra, that's a very good question, by the way. This could also be, this here could be your dienophile, yes. Okay? But then, since you asked that question, there is another aspect of the Diels-Alder reaction that I need to let you know. Generally, for Diels-Alder reaction to work very well, the dienophile must contain electron withdrawing group. You notice that most of the dienophile we give you, they have some carbonyl attached to it, or cyano group attached to it. They must contain electron withdrawing group. The dienophile. So let me write it down. In Diels-Alder, the dienophile usually contain electron, forget that, electron withdrawing. The dienophile usually contain electron withdrawing group. For example, anytime you have a carbonyl attached to carbon-carbon double bond, the carbonyl carbon is an sp2 carbon. It is electron withdrawing. The cyano group is electron withdrawing. So for the most part, the best Diels-Alder reaction is that in which the dienophile contains electron withdrawing group. So to answer your question here, Myra, so if this molecule, in this molecule therefore, since we have this molecule, if you have this molecule here, okay, which would be the best dienophile in this molecule, in this part of the molecule? This here or this here? Exactly. This would be your better dienophile. Okay? So because they will be competing with each other. In that case, the one that contains the electron withdrawing group will be the better dienophile, and therefore the reaction will take place on that carbon-carbon double bond. Okay, let's do question number 6. Oh no, I'm sorry. D. Let's do D. Okay, for D, we have this molecule here. Let me draw that out for you. This is what you have. You have that, and then you have the ester. Oh, no. Okay, that is the product. So what would be the starting material? Yes. Amacillus, right? Okay. So since we have a 6-member ring, obviously that is the product of the Diels-Alder reaction. So you want us to break this here, right? Exactly. So the left part will be the diene. Very good, very good. If that is the case, so we have, that is your diene, right? Where the dienophile?
The right part is going to be a triple bond.
Exactly. Excellent. So what that tells you is that the triple bond could also be a dienophile. Okay. So in this case, the triple bond, which is and that would be your dienophile. Okay. And so both of these, this is the diene, and this is your dienophile. So what this is telling you is that the carbon-carbon triple bond could also act as a dienophile. Okay. Is there any question before we go to the next one? Yes, go ahead. Is that Mike? Okay. Huh? Okay, very good. See, okay, based on what we have here, we say if we clip this here, keep in mind that this will become your diene, double bond here, and we know that you must have the dienophile with at least one double bond, and that double bond must disappear at the end of the process. But since we have a double bond here, that means there was an additional double bond. You see what this is? Because you have this, if it was just a regular double bond, this double bond would have gone. Okay? Okay, so let's go to 6. Okay, so another way the question on Diels-Alder could be asked of you. Okay, the first set of questions we just gave you, we gave you the product, we say give us the starting material. That's a very common way in which questions about Diels-Alder reactions is asked. Another way in which they could ask you, Ambria, go ahead and read this question for us.
Predict the product of the following Diels-Alder reactions.
Okay, so now they want us to predict the product. What they've done, they've now given us the two starting material, both the diene and the dienophile. Now they want us to give the product. Okay, so what will be the product for this? A. Let's do A plus. What will be the product? If you do, yes, David. Okay, so 6-member ring. So we just join this, and exactly. And the bridge. How many carbon in the bridge? How many carbon in the bridge? This is your bridge right here. One carbon bridge, right? Okay, so now we can build bridges, right? So that's a 1 carbon bridge. Now Diels-Alder allows us to build bridges. So now, what is the product? So that's your 6-member ring, right? So we simply draw the 6-member ring. That's 6-member ring, and then of course this is here. This rest of the molecule is here, right? Okay, we have the double bond is here. The bridge will be here, right? And then the rest of the molecule, which is this here, will be here. Okay, David, is that right? Okay. Do you all agree with that? So that will be the product. Now, if you want to be fancy, if you want to be fancy and you want to draw this in a fancy way, right? You're looking at it from the side. Now you're looking at it directly from above, right? Since you want to be fancy, okay, you insist on that. So now you're going to be, it'll be this here. That's your 6-member ring, right? Now you see the 6-member ring, right? Now you have the bridge. You see the bridge? Now then include now the the other part of the molecule should be now this. Oh yes, yes, definitely. I accept that. That's the one you like, right? Forget the fancy one. Okay, so if you want to be fancy, you could draw this. Okay. Okay, let's do B. Anybody want to try B? Karen, are you raising your hand? No. Oh, I thought you were raising your hand. Okay. Anybody want to try B? Okay, yeah. What's your name?
Eric.
Eric?
Yeah.
Okay, Eric.
So there's going to be a 6-member ring.
Okay, just. Okay, let me erase this. So you're going to have 6-member ring with 2 carbon bricks, right? Good. And that would be, so you want us to join this, in essence, since you say you have, actually the way they have it here, they want to confuse you. Let me draw this better. Let's do it this way. Okay. Forget this part, forget this one here, okay? Okay. So now you're saying that we simply going to, let me also draw this one here. Don't forget that this molecule here is the same as I've drawn here. I just want to draw it in a way that it doesn't confuse you. Okay. So you have okay, Eric, so you want us to join what? This carbon?
Yeah.
Okay. You join this carbon to this carbon here, right? And this one to that, and that gives you your 6-member ring, okay? And in so doing, this double bond will disappear, right? And then, of course, this new double bond will be here, okay? So now we have our product. And Eric, you tell us there's a 2-carbon bridge, right? Okay, so the 2-carbon bridge will now be here. Is that correct? You all see that? you see the 2-carbon bridge? Now we're forming bridges. Now do you all see that? Do you want me to draw it in a fancy way? Sean, go ahead. You missed the bridge? Oh, okay. Okay, you missed the bridge. Okay. Do you drive? You don't. You don't want to miss the bridge. Okay, let me take this bridge out. Okay. Okay. Do you follow this 6-member ring? Okay, because we're joining this carbon to this carbon, right? Okay, let's number it because Sinead wants us to number it. So, Okay, so we have, let's say this is carbon number 1, right? Carbon number 2, 3, 4, right? Let's call this 5. Let's call this 6. Okay? So we come here, carbon number 1, 2, 3, 4, 5, and 6. You see that so far? Okay? Now what is missing? We are missing the bridge. Right? Okay, so this bridge here, this carbon here is attached to carbon number 1. Right? Okay, so we're going to take that. Okay, so that is that carbon attached to carbon number 1. And then this other carbon, the second carbon in the bridge, is attached to carbon number 4. Right? So I have this. That's the bridge. Okay? Everybody follow that? Now you do. Okay. Any question? Okay. So now another question here. Let's see. So we've done both of this. Okay, what time do we have? Oh, no, come on. I don't trust you guys. I don't think you guys can be believed. Oh, 7:03. You're trying to cheat me out of my time. Okay. 7:03. We got plenty of time. Okay, so now let us go to question number 4. Okay, question number 4. Okay, so I think for the most part you guys should be experts on the Diels-Alder reaction now. So what I want us to do now is to sort of revisit the reaction that we started the last time we left, which is electrophilic addition reaction. Electrophilic addition reaction. Involving the conjugated alkenes or conjugated dienes. Okay, let's see, who do I want to read this here? Mayo, go ahead and read this for us. Okay. So in this question here, it is a loaded question because they not only do they want you to draw the product, in order for you to do that, you need to know the reaction mechanism. And of course, what you have here, what they have given you, they have hydrogen chloride. And you know that hydrogen chloride, think of hydrogen chloride as essentially as the proton and a chloride. Okay? In this case, this proton here, okay, will be acting as your electrophile. What is an electrophile? Did I hear something? Yes, go ahead. Oh, Blair, go ahead. Electron deficient. Yeah, deficient. Go ahead. Something that needs electron, right? Okay, good. Any species that will attract electrons will be an electrophile. In other words, any positively charged species, or any species that could develop a positive charge, will be an electrophile. Keep that in mind, because we are going to be hearing a lot more about electrophile, nucleophile as we continue, as we progress during the course of this semester. Okay, so any species that is positively charged is an electrophile. Or any carbon or any atom that could develop a positive charge is an electrophile. Okay? So in this case, the proton or the hydrogen here will be your electrophile. And because the pi electrons in the conjugated systems here, those pi electrons will be referred to as your nucleophile. Because what is a nucleophile? A nucleophile is what? Anything that wants to get rid of electron. Very good. Any species that wants to get rid of electron, what's the name? Oh, Shikir? Oh, Shikir, okay. Shikir says anything that wants to get rid of electron, okay? So any species that wants to get rid of electron is a nucleophile. In other words, any species that is rich in electron, any species that contains electron will be a nucleophile, such as a pi electron, a non-bonding electron, those will be nucleophile. Okay. In that case, so this carbon-carbon double bond, or this here, will be acting as a nucleophile. So what do you think is going to happen first? Okay, so this nucleophile here attacks this here. Notice also when I draw the arrow, when you see me draw the two-sided arrow like this, that shows the movement of electron. You also always draw your arrow from where the electron is to where there is no electron. In other words, you drop your arrow from the nucleophile to the electrophile, okay, not the opposite direction. Okay, so now the pi electron will attack this proton here. Of course, that would therefore allow the hydrogen-chlorine bond to break. So now you form this intermediate carbocation. Okay, so now you have, this now becomes your CH3. Keep in mind that right here, this is a CH2. Okay? That's a CH2. So that electron comes here, attaches this carbon to this hydrogen. So now you form a CH3, and the double bond is still here. Now what do you think happens to this carbon now? What happens to this carbon? It becomes a carbocation, exactly. So it becomes a carbocation. Okay, so that is the first step in electrophilic addition reaction to a double bond. In this case, we have a conjugated double bond. So what do we have here? We have a carbocation, which is a secondary carbocation. Secondary carbocation. It is also an allylic carbocation. An allylic carbocation is that carbon atom, positively charged carbon atom, that is attached to a carbon-carbon double bond. So anytime you see a carbon-carbon double bond, and you see a carbon, a positively charged carbon, then you say this is an allylic carbocation. Allylic carbocations are very stable. Okay? It is also a secondary carbocation. So that is the first thing that happens. So once that happens, we could now write a resonance structure for this. Okay? We could now write a resonance structure for this, in which we could simply now move, because of the conjugation, we could move this pi electron to here. Remember, on Tuesday, we show you the orbital picture of this system, because electrons are able to move from one p orbital to another p orbital. Okay. So now, we could draw the another resonance contribution. CH3 is here. So now we now move this to here. That means the positive charge is now here. Okay? So we see I have a secondary carbocation, right? Is that right? It is still a secondary carbocation. Is it also an allylic carbocation? Yes, it is also an allylic carbocation. So not only is it secondary, it is also allylic. Now, in addition to that, we also find that because this positively charged carbon is attached to the benzene ring, we also call this a benzylic carbocation. Now, you will see why the benzylic carbocation is even a lot more stable than the allylic carbocation. Does anybody know why? Can you tell me why? Just taking a look at the structure here. Emma?
Could be that so conjugated?
Yes, because of the resonance conjugation. We could move, because of the conjugation, that is right, we could move all of these pi electrons so that this positive charge could now be shared by all of this carbon on the ring. So that even makes the benzylic carbocation very stable. So what are we saying here? This reaction will proceed anytime you are going to perform electrophilic addition reaction. The reaction will go in the direction that gives you the most stable intermediate carbocation. Okay? So in this case, we are going to go through the formation of this intermediate carbocation. So what will be the product that we're going to form? Exactly. Excellent. Is that okay again? Okay. So now we have the two possible products. Therefore, keep in mind when this happens, when we form the initial carbocation, we also form the chloride. Okay. So now the chloride will now come here, either attack this, or it will attack this. Okay, that is possible. Okay. Now, so now if it does that, what do we get? We could get this product. The chloride is now here, and the double bond is here. Okay? Or we could get this. And the chloride is here. Okay? Now, those will be two possible products. There are some other possible products, but those will not be as stable in terms of the major. If you talk thinking of the major product, the major product will come from the intermediate carbocation that are the most stable. Okay, so this will be your possible product. Okay, so when you go back home, you may want to try some other products of this. Essentially, the first thing that happens is the addition of the electrophile to a carbon-carbon double bond, and then from there you get all kind of resonance, and then you also get the final product as a result of, in this case, keep in mind now that the chloride now is acting as a nucleophile. Okay? Okay, the chloride is acting as a nucleophile in the second stage, attacking the electrophilic carbon here, or attacking this electrophilic carbon here. Yes?
Both the products are considered major products, or is the one that comes from the benzene the major and the other?
Very good. Actually, both, in this case, it's rather interesting. If you look at this, both of these here, if this is the major product, since you asked that question, you know why it is the major product? because that double bond is conjugated with the benzene ring. Okay? And that is why it is the major product. Very good question. Okay, yes. Oh, no, the Mellard was asking me, between these two products, this here and this product, which is the major product? I said, this will be the major product, this here. Because the carbon-carbon double bond is conjugated with the carbon-carbon double bond of the ring. So you have extensive conjugation in there. Okay. Whereas this double bond here is an isolated double bond. Okay? Okay, now let us do one more before we go. Let's see. This is a very important one. Oh, plenty of time. Okay, I will give you back your minute. I think I borrowed 1 minute from you last time, so don't worry, I'll give it back to you. Now, I want us to look at this here. We are not going to spend too much time on this. If you take a look at this here, Sean, go ahead and read this question for us.
The following ultraviolet absorption maximum is eliminated. What conclusion may be drawn about the effect of substitution on UV absorption maximum? Approximately what effect does each added output have?
Okay, very good. In other words, what they've done here, he said the following ultraviolet absorption maxima have been measured, okay? Now, if you remember last semester we did instrumental analysis, we used all kinds of spectroscopy, mass spectrometry, infrared spectroscopy, and NMR. Now, the question that most people may want to ask is, how do we know that most of these molecules are conjugated? We keep saying these molecules are conjugated. For example, if I have this molecule here, if I have that molecule, or I have this here, okay, which of these two molecules is conjugated? This is conjugated, right? How will I know that? The only way I can know that this is conjugated is by using ultraviolet spectroscopy. And for the ultraviolet spectroscopy, we use the light energy in the electromagnetic spectrum that is within the ultraviolet region, which is just slightly before the visible region of the spectrum. And that region of the spectrum, of course, the measurement of wavelengths in that region of the spectrum is somewhere between about 200 nanometers to 400 nanometers. Now, any molecule that will absorb light energy in that region must be conjugated. So therefore, in order for us to determine whether a molecule is conjugated, we simply run the ultraviolet spectroscopy. If it absorbs energy in that region, then we know if it's conjugated. Okay? Now, if it does not, then we say it is not conjugated. So what we use ultraviolet spectroscopy to do is to measure or to determine conjugation in a system. So that is in essence what this question is trying to get you to do. Now, of course, the more alkyl substituent you have on a carbon-carbon double bond of a conjugated system, the greater the ultraviolet absorption. So you don't really need to go too much into that. The take-home message here is the UV spectroscopy will allow you to determine whether a molecule is conjugated. If there is absorption in that region, then it is conjugated. Okay? That's all you need to know. Now, having said that, let us now go to this problem. I don't know whether you can read this. I know, Jessica, I know you got very good eyes. Can you? Okay. I told you she got good eyes. Go ahead.
What's the matter of has the odor of towards the other, and that burn smells like lemon. Lighting has no ultraviolet absorption, maximum of 200 milliliters, and orange is a kind of product having hydrogen and catalyst. Ozone license of lighting followed by zinc, uric acid treatment, yields formaldehyde, and the nitrogen catalyst.
Okay, very good. Okay, this is what it said. This is what Jessica has just given you. You have a molecule. The molecular formula of this molecule is C10H16, right? It's called lamolin. And when you perform ozonolysis, step 1, ozone followed by zinc, you get this set of products. These two products, that's what you get. That is what that is telling you. Okay, now, it also tells you that when you take that same molecule, let's call this molecule A. So let's call this B. So when you take that molecule A and you perform hydrogenation in the presence of some kind of catalyst, let us use palladium. Okay, you get molecule B, formula C10H20. Okay. Now it now also tells you that molecule B is an acara molecule. When we say acara molecule, what does that mean? It is optically inactive, right? In other words, this molecule will superimpose on its mirror image. Very good. So those are the basic information they've given us. Now they're telling us, give the structure for compound A and compound B. Another piece of information they've also given us is that this molecule does not absorb light energy or ultraviolet energy. Okay, so what does that tell you? It is not conjugated, right? Exactly. So those are the three pieces of information they've given us. So this molecule does not absorb UV light. In other words, it is not conjugated. And they're also telling us it reacts with ozone to give this here, and it reacts with hydrogen to give this. Okay. Now, what do we make out of that? Okay, so we have, let us start off. We have compound A. Formula is C10H16. What is the index of hydrogen deficiency? Index of hydrogen deficiency Emma just told us 3? Right, okay, very good. Now for those of you who are not in my class last semester, the formula for index of hydrogen deficiency is this here, number of carbon atom in the molecule minus number of hydrogen atom in the molecule divided by 2 minus number of halogen in the molecule divided by 2 plus number of nitrogen in the molecule divided by 2 plus 1. Okay, that is the formula you use for index of hydrogen deficiency. Of course, some of you may be able to do this without the formula, but when you have a very complicated molecule, this formula does come in very handy. Now, if you use this formula here, of course, this carbon is the number of carbon in the molecule. Okay, the hydrogen is the number of hydrogen in the molecule. Okay? If you use that formula, just as Emma just told us, the index of hydrogen deficiency is 3. So what does that mean? Index of hydrogen deficiency of 3, what does it mean? It might 2 double bonds, a ring, or triple bond. Excellent, excellent, great. Okay, so we know that we have all kind of combination here. Now, this reaction here, hydrogenation, gives you compound B, C10H20. Okay, now what is the index of hydrogen deficiency of compound B? What is it? 1. So what does that tell you about compound A? No, must have a ring. Because the index of hydrogen deficiency of compound B is 1. Okay? Because if it is 1, that means the hydrogenation does not reduce a ring. Okay? So all of the double bonds are gone. So what this is telling us is that compound A must have a ring. It must have either a double bond, 2 double bonds, or a triple bond, right? That much we know. Now, it now tells us, don't worry, we're going to finish this in 5 minutes. I only have 2, wow. Okay, we finish in 2 minutes. Okay. Okay, now, if you look at this, can I borrow another 2 minutes from you? No, okay, let's look at it. Okay, let's go fast. Okay, the most important information here is the ozonolysis. Okay, we know that we have 2 double bonds, we have a ring. Okay, now, ozonolysis said we have this formaldehyde. Keep in mind that everywhere you see the carbonyl group, that came from the cleavage as a result of ozonolysis, right? Okay, so let us now put the pieces together. So I will do this. I will say, okay, this CH3 here, carbonyl, right? CH2, I'm trying to write this here, right? Okay, and then CH, okay, and then you have CH2, and then you have C carbonyl and hydrogen, right? And then here you have carbonyl. Okay, I'll do this. Okay, I'll say this formaldehyde here. Okay, this formaldehyde here. Okay, it is possible. What if I say I take this off? You could do all kind of permutation you want. So now I'm going to put C here. Okay, so cleavage of this with ozone will give formaldehyde, right? And this rest of the molecule. So far so good. Okay, now then I say, okay, and now I have this carbonyl and this carbonyl. They must be from a double bond, right? Okay, so I take this off, then I join it together. I have the longest double bond in the history of chemistry, right? Then I have this double bond here. So that is the only way that would, okay? You see that? Now, since that I've formed the molecule that hopefully that is the molecule that I want. If it doesn't work, you go back to another permutation. So now let us now write this in a fancy way, right? How many, this double bond here is 1 double bond, okay? How many carbons in this ring? 1, 2, 6, very good. So it is, yeah, I think you want to get out of here. And you want to go home, that's why. Okay, so we have 6. Yeah, it's a 6. I didn't even ask the question before. It's a 6. Okay, good. Okay, so now we have this. That part, okay. So since you say 6, so where would that be now? Okay, that would be this carbon. Okay, let's follow this. This carbon here would be this carbon right here, right? Okay, so therefore the double bond must be here. So I then have my double bond is here. Okay, if that is the case, if I clip this, that would be the aldehyde that is on this side. Therefore, this here, this methyl group must be here. Okay, and we solve the problem. Okay, this is not a conjugated molecule. That is why it does not absorb UV light. Okay, anyway, these are the kind of problems you should expect to get when you do problems in this chapter. So I will see you on Tuesday, and then I will be emailing you in terms of, well, by the way, I don't need to email you. The next chapter will be chapter 15. So enjoy the rest of your, enjoy your weekend, and I will see you on Tuesday.